Okay, good morning, guys. So, any question about homework or the lecture? So if you don't have a question, let's go to discussion handout. Okay. The first theory is about the weighted square. So it's under assumption A3. Okay. And if this matrix is symmetric, then we can say that the beta H is equal to beta V inverse, beta H inverse. And this can imply that the beta H is blue. And if ASO is follows lower distribution, then the beta H is UAV. Okay, so to this we will show these two in the exercise. And next is some notation and the property of GLN. Okay. So I think as long as you know the notation of GLN, you will be fine. Yeah. For the exam. Yeah. Okay. So this question is this first question is blue. Okay. Okay, how about let's do question 2 and 3 first. It's about these two property. Yeah. So it's why we have this, we can imply this, and why this can imply this is blue and this is UAV. Okay. Let's do 2 and 3 first.
Hi.
Hi.
I have a question. So I'm looking at slide 13 of lecture. Let me see, lecture 10.
You say okay. Slide 13. Okay. Yes.
So more or less in the middle of the slide, it says that it is blue because the variance of this is the identity.
Okay. Yes, that's right.
Um,
Okay. Yeah, that's a. Oh, I know how you point. What's your point? Okay.
no, I'm thinking, yeah, is that the case? Like, I guess that it is blue. So that this means it's blue because it's the smallest possible, I don't know, covariance matrix in some sense. I am not sure.
Okay. Uh, the way they say this is okay. I didn't. He said it's blue is because the if you consider v negative 1/2. Okay, I didn't use this, but this is. So here is okay. First we know that if y is equal to plus s, first if s is follow mean and sigma square, then the beta head is blue. And it also said that okay. So what he do here is he multiply this. So okay. And this one is Kasi. And the Kasi is minimal variance sigma square. And then he can apply this property because this is minimal variance sigma square. Okay.
Okay, yeah, makes sense.
Okay, then this way will be very fast. Yeah. Okay. Okay. I didn't look at nature carefully. Okay. Hmm.
So for problem 2,
Okay.
for problem 2, we know that beta hat sub V inverse, the weighted least squares estimator, is always the blue, right? That's always true.
This one, you should under the,
No, not that one. The weighted least squares estimator is always the blue, right?
yes, under assumption A3, it's blue. Yeah. And the V inverse should be long. Okay.
So problem 2, is there any is the argument just for problem 2 that the weighted least square estimator is the blue, and so if the non-weighted least square estimator is the blue, then it has to be equal to the weighted least square estimator. Is that it?
Yes.
Okay.
Yes, you can say that. Yeah. So the key this one is important is because we don't know V. So if these two are equal, then we can say we can have the estimator, and we can say it's blue. Yeah. So you can say like if V is known, the beta hat V square is blue for all like the function A transfer beta. Okay. How do you say this? And A can be a function of V. Okay. How about let's say like this? It can be a function of V transfer Y, and this is equal to L transfer beta. Okay. So this is the set of a linear unbiased estimator. Okay. But when we say this is blue, the candidate is much smaller, so it's just this. So the A cannot be the function of V. Yeah. Okay. So what I want to say is when we say this is blue and this is blue, we consider on a different candidate set. Okay. And this one, the candidate set of this one is much larger than this one. So we can say this is blue will imply this is blue when these two estimates are equal. Yeah.
I'm not sure I followed that argument. So there's a larger number of candidates for the weighted least square estimator than there is for the least square estimator.
Yes, because in here we assume V is known, and under this, when we say this is blue, we didn't assume V is known. Yeah. We don't leave V is known. Yeah. Okay. So
so you can't just argue that the weighted least square estimator is the blue, and therefore if the regular least squared estimator is the blue, it must be equal to the weighted least square estimator. That doesn't, that's not true.
I think that, yeah, I think that's right. Yeah, I just want to tell you more about why, yeah, why this is work. Yeah, I think as long as say this is blue and these two are equal, I think that's enough. Yeah. So,
Yeah, exactly, Albert. I think it should be unique, right?
oh, you said blue should be unique? Yes,
Yeah.
blue estimate is unique. Yeah. Sorry. Yeah, Albert. Okay. Hmm. So V is unknown. Uh, when these two estimators are the same, so that means I think what here I want to say is when you say estimate is blue, you have to be careful what is the candidate set. Yeah. So when we say the weighted estimate is blue, here we say that's the variance of the L transfer beta has be yours. This one is smaller and equal to the variance of A, and the A can be a function of V, and also they have to satisfy the AV. The average of this is equal to L transfer beta. And when we say beta hat is blue, this means the variance of this smaller for every function A transfer B, and we need a condition that the okay. So when we want to say the blue of this implies the blue of this, the definition of these two blue is not the same, so we have to be careful. Yeah. And yes, but here we want to use the blue of this one to imply the blue of this one. And you can see that the candidate cell is much larger. So you can directly imply this one, yeah. So if in some general case, it may not be true, but this one is yeah. So this is why I want to mention this, yeah, okay. And I see in the exam, you can just say you can use this theory, yeah. So you can say, because this is symmetry, so this is blue, yeah. And so the question is, why if the candidate said this is much larger than this, can this argument also be true? Yeah. So I don't know that, yeah. Yeah. Okay. So okay. Yeah, originally why I did this question, I go from the definition to show that the beta hash is blue. Yeah. 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 But I think in the nature knows that way is much faster, but yeah. Okay. So we know that beta heavy inverse okay is arc mean of this. So for any, so if given, and we want to show that proof, okay, so given any unbiased estimator, so the C transpose Y is unbiased for L transpose beta. Okay. And we want to show that the values of the L transpose beta, okay, this one is smaller than values of, okay. Okay. So first, we know this one is equal to S beta. And this is equal to L transpose beta. So they can imply the sin transpose of X equal to L transpose. Yes, okay. And also, okay, calculate this. The values of L transpose beta has P inverse. This is equal to the values L transpose beta has V inverse minus this plus this. So this is equal to the values of plus the values of sequence Y, and the covariance term plus 2 values of okay. Okay, so if this term is 0, then the whole thing will be, then we can say the base of this term is larger than the base of, is smaller than the base of this term. Okay. So let's say this is star. Star is equal to this. Okay. That is because the this term is meaning okay.
So I think I don't know. Maybe what you're doing will work out fine, but I think you are trying to use the same strategy as in the slides. And in the slides, they start calculating the variance of C prime of Y.
Yes, I think both way can good. Okay.
Okay.
Yeah, can work. Yeah. Okay. Sorry, I think I made some mistake. Yeah. This is oh yes. I go with a wrong direction. Yeah. So this should be C times of Y. Yeah. And yes, because we want to show this one is larger, so it should be here. Okay. Yeah, thank you. Yeah, so this is a C transpose Y minus. Okay, so it should be values of this term And this is the same, but it's this is okay. Yes, I think I basically follow. You mean yeah, it's the proof for Gaussian Markov theory. Just here we consider the different estimates. Yeah. So this should be yes. So then this is equal to this. So this is equal to this. Here, sorry, here's no x. Okay, L transpose this. Okay, and L transpose can be equal to C transpose X. So it can be, this can be C transpose X. Can be C transpose X. This is C transpose X. Okay. And so the first term will be the C transpose Y minus this. This. And the second term is also is C transpose this. We can look at like this. Okay. Yes. So this term is the transpose of this term. Yeah. So internal we can have we can change this to change y into, see, it's not good. Change y into the S beta. Okay. So got change y equal to S beta, and yeah, S change y equal to S beta plus the plus ASO. And so the next term we take an expectation will be S beta beta transpose X plus sigma square identity. Okay. And what is? Okay. This term is 5 needle, but this term is we have this and this. So okay. I think this is not a good idea. Yeah. Yeah, sorry, I will fix it. I think I must do something wrong in the beginning. Yeah. I just realized if this term multiply this term is not zero, but it should be zero. Yeah. Okay. Okay. And in the question 3, we can use a similar argument by saying the beta hat is this is UAVE, and these two are the same, so the beta hat is also UAVE. Yeah. Okay. Okay, and okay, in question 1, this is okay. And I just realized that the question 1 is the totally the same as the example in the nature. Okay, but this application of this property. So why this is the same use covariance never. Okay. So maybe I should use covariance. Okay. Minus C transpose X. And Try to obtain. Okay, let me see. Oh, okay. Yeah, you're right. Yeah, thank you, Albert. Yeah. Okay. Yeah. Sorry, I had to prepare more. Okay. About the question one is the, so we want to show this is blue. Okay. And we can, what we want to use is use the, find the, this property. Is symmetric. And then apply the theory. Okay. So the first thing we have to define what is V. Okay. So Y is equal to S beta plus SO. But we say the beta is a random vector. Okay. It's depending on SO. Okay. So and the mean is beta. Okay. So how about I say the random vector is B. Okay. And this is equal to X beta plus X B minus the beta plus SO. And you can say this one is a new estimator like the eta, new noise that's eta. So this part is random. Okay. And this is random. This random. Meaning though. Okay. So we want to find the variance of eta, which is, this is V. So it should be equal to X transfer variance of B X plus, sorry, sigma square. Okay. So we multiply this. X variance of B X transpose plus these two, so it's a sigma square X transpose X equals X transpose. And these two can be cancelled, so it should be the X variance B X transpose plus sigma square. Okay. So you can see this is symmetry.
I'm a bit confused
Okay.
because so in your first line, like in red, you're saying more or less you're treating the thing in between parentheses B minus B as if it was B, but it's not B, it's B minus B. So if you have xb plus epsilon, the variance of that is x variance of b x prime plus the variance of epsilon. Oh, plus covariance term. Maybe it's because of that, maybe because of the 2 times covariance, or I don't know. I didn't.
Oh, okay. You mean this time?
Yes, I didn't follow that.
Oh yeah. sorry. Yeah, sure. You're right. We should have the convex matrix. Yeah, but the question said the convex matrix is zero, just the correlation of B and so it should be have the X, B, and S. Okay. So
Yes, but then the question is, we don't have xb, we have x of b minus b. Or I'm missing something maybe.
oh, like this. Okay, X of B minus B.
Yes, that's what we have, I
Okay.
think.
So
But then we should maybe also have, instead of variance of b, maybe variance of b minus b or something like this.
okay, you're right. So sorry, I'm not say carefully. So the mean of this is beta. Okay. So
Okay.
this is the only random part. So that's the reason why I want to do this to make sure the noise is mean zero. Okay. So originally these two are all random, but we want to make sure the error is mean zero. Okay. So we minus the S beta and plus S beta. So this is fixed. It's a constant. Okay. Constant. And this is noise. Yeah, that's a good point. Yeah. Yeah, sorry that. Okay. Okay. So and here we apply the this is needle. Okay. Okay, thank you. Okay. So we have this, yeah. Okay, so then we have this symmetry, then we apply theory. Okay. Okay. And the next question is okay, actually this question is exactly the same as the homework. Okay. And yes. For the GRN question, you only need to know the notation, and I think then the question will not be harder than this one. So just may ask you to do some find the negative equation and like the do some derivative. Yeah. Okay.
So I tried to do this question in the homework. I was a bit confused about a couple of things, but maybe you will clarify. The first one is when they say obtain the likelihood
Yes.
function. Yes, the likelihood equation. Do they mean likelihood really, or log likelihood is fine, or do they really want the likelihood function equation?
Okay. In here they want to find the derivative log likelihood. Okay. So because we solve beta by this.
Yeah, sure. But I try to. I mean, on the slides there's already this equation, but it's the log likelihood. I don't know if that's fine to use the log likelihood.
Yeah, it's fine. You can use log likelihood. So
Okay, and then my second question is when they say the matrix of second order derivatives, and they just show me like one term. Like normally a matrix has, I mean, it depends on how many variables you have, but if you have, oh, it's because there's only one variable, or I was a bit confused because I was expecting like a matrix and not like a summation, but maybe it's because there's only
okay.
one variable or something.
Yeah, it's matrix. This is matrix. you can look at this. This is X and X transpose.
Oh, that's a matrix. Oh,
Yeah,
okay.
yeah,
I see. I see.
yeah. So this, yeah, sorry, this the notation is confusing. Yeah.
No, it's true. It's true. I didn't pay
That's a good
attention to
point.
it.
Yeah.
Okay. Thank you.
Yeah. So usually we say the likelihood equation is we use the log likelihood. Okay. So it's okay. So nice. Okay, so let's try to do question A. Okay. Okay. So we know the GT is log T. So that means it's a canonical link. So because G exponential is equal to E times T. Okay. So we know Yi is follow this exponential X transpose beta and Yi minus E exponential Si transpose beta. Okay. So the likelihood function will be the product of this and the log likelihood function is this summation and also the rest of term. Okay. Yeah. So we can have a summation here. So we want to find the first derivative. So this is Lino and this is YIXI transpose minus this and SI transpose. Maybe I usually write it as a counter, so it should be like this. Okay. So this is a likelihood equation. So yeah.
Maybe a basic question, but how do you know? Because I have difficulty knowing when I have to say x or x prime when you take like the derivative. So you wrote x instead of x prime. So how did you know that you had to do that? Like I'm not very familiar with this type of derivatives.
Okay. The reason I do that is I always write the gradient of this as a row vector. Yeah. So the SI is a row vector. Yeah.
Okay.
Yeah. So like the SI transpose will become a row data. Yeah. So the derivative of this is a row vector. So I write it as a SI. Yeah.
Okay. Okay.
So this is also a row vector. Yeah.
Okay. I see. Thank you.
A color. Yeah. Color. Yeah. Okay. Yeah, the notation go to the metric will sometimes confusing. Yeah. Okay. So we can do the second derivative. So this is also little. I think the best way to measure this is after you do something calculation, you have to go back to check the dimension. Yeah. Yeah, so if I write it as this one, then that would be wrong because the dimension is 1. Okay, so okay. This question A. And also B, just some series of calculation. But you have to be careful of GT is not a canonical form. So we have a GT is equal to this. So that means we know G exponential eta I. This is equal to beta transpose Si. So they will have the 2 eta I just Si. So the eta I will be 2 and take the log. So it will be eta I equal to 2 log beta. Okay. So then we can have the negative function yi is follow the this. And exponential. Okay, so we plug in the eta as the this, so it should be 2 log. And the second term is exponential of eta. So yes. Okay. So we can let's derive the log likelihood. Tutorial and the second term plus this. And minus this term. Actually, this term can be beta transpose like this. Yeah. Okay. Yes, everything is fine. Let's find the first order derivative. So this linear and this is 2 log beta transpose Si. And take the derivative on the beta, so you add to Si here. And over 2, so we can cancel the 2. And here is the summation. Two multiplied 2, okay. Yes. Okay, so the equation will be like this. Okay. Yeah, actually, only use this, then you'll be able to calculate. Yeah. So like this notation sometimes confusing. Yeah. So once they give you a link function, then we can calculate a log likelihood. Okay. Okay.
Sorry, I need to go now, but in the derivative of the last term,
Okay.
is there like an xi missing maybe? Because you bring down the exponent. Oh no, because okay, because there's a no, yeah, is there something missing there? So you bring down
Yeah.
the exponent.
Yeah, you're right. Sorry. So here, yeah. So here I derivative over beta, so it should be, yeah, this time is wrong. Okay. Yeah, thank you.
I was also talking about the last one actually. That
That's
maybe there's an xi missing, like a term
oh
missing.
yeah. This is
Okay, yeah.
actually this time is wrong. Yeah, sorry. Yeah, the both time is wrong. Okay.
It's okay, no worries.
So we derivative over the log, so it should be this. Yeah, and the chain rule, so it should be like the SI. Okay. Yes. So the solution will be, we cancel these two. Minus the, okay. Okay. Okay, we still have the few minutes. So, any questions so far?
Would it not be an xi over 2 on the far right as well?
On the far right as well. You mean here? This time?
The xi on the third term. Right, when we took the derivative of the inside of the log, we got xi over 2. Why would we not get an xi over 2 taking the derivative of the inside of the square?
Okay. Oh yeah. Yeah. Thank you. Yeah.
Okay, great. Thank you.
Yeah. Yeah. Over to yeah. It's like this. Okay. Yeah, see the next few minutes, let's talk about let's talk about this question. Okay. So we want to show that this symmetry if only if this is hold. Okay. Yeah. So we have the Vx. Okay. This way is it's easy. It's much easier because we know that this is equal to V because that is symmetry. Okay, so it should be equal to, okay. So we can multiply x in here in both sides. Okay. So these two can be canceled. Then we can have the Vx is equal to x. And this is B. Okay. The hardest part is the unordered, the only if part. Okay. So we have the, okay. We want to show this is symmetry. So okay, let's look at this. V is equal to so okay. Sorry. So here let's define P as equal to x transpose x. Transpose. So it's a projection matrix. Okay. So Px, we want to show this is symmetry. So we can say this is V Px plus I minus x. So if the V I minus Px is little, then we can say this is symmetry. Okay. Okay. So that's V minus Px. Okay. So like this. Okay. So is this 0? Okay. And then this is equal to x. And Vx, this can be equal to Px. Okay. So then this is 0. Okay. Yeah. The Vs is equal to V transpose x. So yeah, so we can say x transpose V is equal to x transpose V transpose because the V is variance matrix. So this is equal to Vx transpose, and this is equal to SB transpose. Okay, so this has transpose here. Okay. Yeah. And this is 0. Okay. So, okay. I think that's today's discussion. Okay. Yeah. Okay. If you need any help, please let me know. Okay.
Could you explain how you know that last term is equal to 0?
Okay. So this is a projection matrix. Okay. So you can know that the x transpose PS equal to x. Or if you, and this can be like the PS is equal to this. Okay, so you can cancel these two terms, they're equal to x transpose. And the S transpose I is equal to S transpose. Yeah.
Okay, that makes sense. Thank you.
Yeah, you're welcome. Yeah.